Today, you are going to go on an unforgettable journey in which you will understand the geology of the planet Earth. You will travel back in time to understand how our planet was formed. You will understand the different layers of the geosphere with its different characteristics, finding out the insanely high temperatures of the Earth's core. You will also learn how the rocks of our planet are created, modified, and destroyed in an endless cycle. You will also discover how evidence showed us that the continents of the world move and how they do so. You will know how volcanoes come to exist, how mountains are formed, and why earthquakes happen. Today, you're going to get your MS in geology. So prepare yourself and turn on your neurons, because you're not going to be a scrub when it comes to Earth geology any longer. Today, you are going to be a master. About 4.6 billion years ago, in our region of the Milky Way, a nebula, which is a large cloud of dust and gas floating in space, collapsed upon itself due to its enormous mass. The materials concentrated, and due to the force of gravity, the heaviest one stayed at the center, beginning to create the sun. The great mass of that nascent sun caused a protoplanetary disk, flattened and rotating around the sun. And then the planets began to form. The theory of planetesimals is the model that best explains how this could have happened. The force of gravity caused the dust and gas floating around the sun to begin to clump together. The bigger the groupings became larger and larger the more mass that they had, attracting more dust, more gas, and more rocks, creating a dynamic in which what were initially just many small particles ended up becoming protoplanets and subsequently planets on their own. For hundreds of millions of years, planets like Earth were attracting the enormous amount of meteoroids that still orbited around the sun, and there were so many impacts that turned the planet into a red-hot hell. This is how it is explained that the interior of the Earth is so hot. The interior of the Earth has a lot of molten iron, but also has many radioactive materials. Finally, we have to consider that the Earth was a molten ball in its origins. When the meteorites stopped impacting, the outer layer gradually cooled, which caused the crust to eventually become a solid and cold layer. But as everything cools from outside to inside, there is still a huge residual heat from when the Earth was formed, which, combined with extremely high pressure and radioactivity of the core, causes the temperature at the center of the Earth to exceed 6,000 degrees Celsius. This is how we understand today's Earth, whose interior is studied based on two models that name distinct layers. The static model focuses on studying the chemical composition of each layer, since the minerals present in each layer vary as we go deeper. And the dynamic model focuses on studying the mechanical behavior of those materials, that is, whether they're liquid, viscous, or solid. So let's start with the static model. The outermost layer is the crust, with a thickness ranging from 3 to 70 kilometers of hard and rigid rock. There are two types of crust, oceanic and continental. The oceanic crust, formed by basalt rocks, is denser and heavier than the continental crust. That's why when an oceanic plate collides with a continental plate, it's usually the oceanic plate that subducts back into the mantle. The oceanic crust is also younger than the continental crust. In fact, the oceanic crust is continuously regenerated through the larger rifts that separate the continental plates. The continental crust is lighter and is made up of granitic rocks that may be covered by sedimentary or metamorphic rocks. It is much older than the oceanic crust, but currently, continental crust is not forming anywhere on the planet, so its formation cannot be studied and its origin is not very clear. The next layer down is the mantle, which is molten and has a thickness of about 2,900 kilometers. The upper mantle is characterized by the presence of minerals such as olivine, and the lower mantle is dominated by minerals such as silicates. The deepest layer is the super famous giant like button. Okay, I'm kidding. But seriously, if you are enjoying this video, please don't forget to click like and subscribe. Something as simple as this is very, very important for the channel. So thank you very much if you do that. Actually, the deepest layer is the core, made up of iron, nickel, and the super heavy radioactive elements. The outer core, due to the pressure and temperature, is very, very liquid, but the inner core, which extends all the way to the center of the Earth, 6,378 kilometers deep, is subjected to so much pressure that the molecules are so tightly packed that they cannot even be in a liquid state, but rather return to a solid state. In the dynamic model, the outermost layer is called the lithosphere, which is characterized by behaving in a fragile manner when subjected to deformation, meaning that it breaks apart. The lithosphere reaches a depth of between 100 and 250 kilometers. The asthenosphere extends down to a depth of 350 kilometers, and due to having a higher percentage of molten rock, it can move independently of the lithosphere. The next layer is the mesosphere, which encompasses the rest of the mantle. And finally, the endosphere corresponds to the core, which is divided into the same layers as in the other model: the outer core, which is liquid, and the inner core, which is solid. But what if I tell you that the deepest hole ever dug by humans is only 12 kilometers deep? How is it possible that we know what is happening at a depth of 6,300 kilometers? Well, my friends, that's where human intelligence and science come in. We don't need to dig to learn all of this because there are indirect ways to deduce what is happening down there. It was in the Soviet Union where the super deep borehole of Kola was drilled, reaching a depth of 12 kilometers. The rock reached temperatures of almost 200 degrees Celsius, causing it to become viscous, saturated with water and hydrogen, and constantly collapsing inside the borehole. After several collapses, it was realized that the rock was so unstable that drilling could not continue, so the project was simply abandoned. However, even though excavating to the center of the Earth is not possible, its composition can be studied through seismic waves, as the wave velocities change depending on the type and state of the rock. The first seismographs, devices used to record earthquakes, were invented in the 19th century, and by the early 20th century, they had spread to many countries around the world. Two types of seismic waves have been identified: P waves and S waves. Scientists had theorized that if an earthquake occurred in one place on Earth, the seismic waves should travel in a straight line at the same speed through the crust until they were recorded in other places. This was the theory, but it was not being confirmed. In reality, anomalies like this were occurring. This could only mean that the Earth was not uniform in its interior and must be composed of different layers. In 1909, a Croatian scientist named Andrija Mohorovičić was the first to explain what was happening. He realized that when an earthquake occurred near the surface, there were waves that traveled near the surface and others deeper down. The ones that traveled closer to the surface arrived more quickly at seismographs located closer to the epicenter of the earthquake, but surprisingly, the deeper waves were the first to arrive at the farthest seismograph. This could only be explained if there was a difference between the properties of the upper zone, the crust, which was solid and rigid, and the mantle, which was viscous and more plastic. The waves took longer to penetrate the deeper mantle, but once they succeeded, they could vibrate more quickly, eventually arriving more quickly at the farther points. This was how the crusts, mantle, and boundary between the two layers, the Moho discontinuity, were established. Shortly after, in 1914, it was Benno Gutenberg who discovered that at a depth of 2,900 kilometers, P waves experienced a distortion in their direction, and that S waves simply stopped. They couldn't penetrate the area at all. The study of wave behavior had shown that P waves underwent variations depending on the state of matter, and that S waves couldn't penetrate liquids. In this way, it could be deduced that at that depth, the matter there must be in a liquid state. A new layer had been discovered, the core, which was completely molten. In the boundary between the both layers, the Gutenberg discontinuity. Finally, in 1936, it was Inge Lehmann who discovered a final deviation in the deepest part of the core, indicating that it was in a solid state, although it seemed illogical. At the time, there was not enough technology to accurately analyze waves that reached such depths. Something was needed that could create a very powerful tremor, so that its waves could be studied accurately. And that something was not long in coming. During the 1960s, the US had already filled the planet with seismographs and took advantage of their nuclear tests to lend a hand in science. Now that the exact time and location of the explosions could be known, waves could be studied with millimetric precision, and that's how it was possible to identify that this new layer, which could be named the inner core, began at a depth of 5,120 kilometers. Basically, studying the way the waves move and comparing it with laboratory simulations, where the speed of waves in each mineral is tested, is how it is possible to infer which minerals make up each layer. All of this is done using logic, our best tool. Using the brain to deduce what we can't directly see. So now that we know the layers of the Earth, it's important to understand the basic material of the crust: rocks. This is where we live. This is Earth's crust. The crust is made up of many rigid sections of rock. Simple enough, right? But in reality, it's quite a bit more complex than that. We can find areas made purely of rock, while other areas are covered by sediments like sand. And when you look closer, many rocks don't even seem that similar. Some of them, like sandstone, look as though they were made of small grains of sand. But other rocks, like granite, have very different crystalline structure. What is even more intriguing is that on a larger scale, some rocks are organized in large, flat, parallel layers. And even stranger, in some cases, these layers are folded. How can a solid rock fold? Since antiquity, many naturalists wondered how rocks are created. But since the process is so slow, it's basically impossible to see with the naked eye, and the answer wasn't easy for them to find. In the late 18th century, a scientist named Abraham Gottlob Werner proposed a theory called Neptunism in honor of the Roman god of the sea. His hypothesis was that the primitive Earth was made primarily of water, but this primitive water held substances that settled down through sedimentation, forming the planet's solid sphere. Of these layers, granite was the heaviest and the most durable, so it deposited first, forming a solid floor. Other newer layers of sediments deposited on top of it, including the abundant fossils of living animals. So, according to this theory, this is how the vast majority of the planet would have appeared. Volcanic activity only had a marginal influence by altering the continents slightly and introducing additional sediments and volcanic rocks. Subsequent minor floods contributed further to the layers, ultimately forming the majority of rocks as a result of particles precipitating from the water. Well, to a person from his time, this theory sounds good, but actually, it was impossible. Werner missed an important consideration because he didn't try to calculate whether the total amount of water on our planet could even hold such a huge quantity of dissolved particles to form the Earth. Even though the oceans appear gigantic, taking up over 70% of the Earth's surface, the quantity of water is actually not really that much. As you can see in this graph, This is the planet Earth, and this is the total amount of water covering it. So, as you can guess, this tiny quantity of water cannot hold the particles necessary to create such a huge planet. In addition, today we know that the quantity of water on Earth is always the same. This is a part of the water cycle. Our planet is neither receiving nor losing any water from any other sources. So water is in constant movement around the Earth, but the quantity of it always remains the same. So these floods proposed by Werner were basically impossible. Needless to say, this theory did not convince everyone. Finally, it was James Hutton who proposed an alternative theory called Plutonism, in honor of the Roman god of the underworld. Hutton's hypothesis was that the main cause of the rock formation was actually heat provided by the Earth's interior. He suggested that the origin of all rocks was the magma located in the interior of the planet. At this time in the 18th century, scientists had not discovered that the Earth was a gigantic ball of molten material covered by a thin layer of solid rock yet. So this theory was also kind of controversial. Hutton proposed that the islands and continents had emerged thanks to volcanic activity from the bottom of the ocean floor. So all the rocks covering the planet had its origin in this primal magma of sorts. Subsequently, rocks would be eroded, turned into sediments, transported and deposited, where the Earth's heat could transform the sediments into new, different rocks. And well, Hutton was really close to the right answer. Certainly, magma was the primal matter that formed all of these rocks, but since he didn't know Earth's structure and about plate tectonics yet, he couldn't really explain how rocks emerged aside from a bit of volcanism here and there. The base of the rock cycle is magma, the molten material that is in Earth's interior. When magma reaches the surface, it cools down, producing igneous rocks. Igneous rocks are divided into two main groups. If they cool down under the surface, they will cool more slowly and be exposed to higher pressures, leading to bigger crystals, creating what we call plutonic rocks, such as granite. On the other hand, if they make it to the surface, like in a volcanic explosion, they will cool down much more rapidly and won't have time to develop these large crystals. We call this other type of rock volcanic rocks, such as pumice. But what happens when these rocks are exposed on their surface? The agents of erosion start attacking them: rain, ice, or even living organisms. They attack and break down these rocks, fragmenting them into smaller and smaller particles. These small particles are called sediments. Sediments are carried downwards by wind or water in a process called transportation, until they eventually get deposited in some kind of low point called a depression. And speaking of depressions, that's exactly where I am when I have a giant pile of geology exams to grade. These are another kind of depressions. Basically, they're low points where gravity will bring all of these sediments. These depressions can be valleys or plains, but in general, sooner or later, the sediments make their way out to the ocean. And here's where things get really interesting. Near these coastal areas, large amounts of sediments tend to accumulate due to rivers or other sources depositing them there. The weight of the sediments and the pressure of the weight of the ocean water above them compress and compact them, forming layers. When the sediments are under an immense pressure and some magma infiltration raises the temperature nearby, they start experiencing some changes. Under extremely high pressure and temperatures nearing 200 degrees Celsius, the rocks undergo the process of diagenesis. The particles compact, cement together, or recrystallize, transforming into sedimentary rocks. The name, obviously, means that they are made up of sediments.
Bruh.
For example, gravel, turns into conglomerate. Sand turns into sandstone. And limes turn into, you guessed it, likes. Okay, sorry, that was bad. I'm kidding. But if you are enjoying this video, please don't forget, click like and subscribe to the channel. Something very simple like this goes a very long way to help the channel, so thank you so much if you do that. Actually, limes turn into limestones. These rocks, buried under a deep layer of sediments, can stay there for millions of years. But if two tectonic plates collide together, they can be pushed back up to the surface. Once they're on the surface, they will be once again exposed to the agents of erosion, so they can be eroded and turn into sediments once again. However, sometimes different things can happen. If the sedimentary rocks remain buried and the temperature exceeds 200 degrees Celsius, it starts a process called metamorphism, which in turn produces metamorphic rocks. Metamorphism comes from two Greek terms, meta, that means change, and morph, that means shape. So these rocks change their properties and turn into new rocks. Just like the morphing from the 90s.
Alright then, it's morphin' time! Dragon Sword! Mastodon!
Pterodactyl!
Triceratops!
Saber-tooth tiger!
Tyrannosaurus! Yeah! We're back! We're ready to morph into action!
So these new rocks are more compact and crystallized than ordinary sedimentary rocks. For example, sedimentary sandstone transforms into metamorphic quartzite, limestone turns into marble, and conglomerates transform into metaconglomerates. The last one is fascinating because you can see how in these metaconglomerates, the gravels get completely flattened due to this pressure. Igneous rocks too can become metamorphic rocks if they're subjected to sufficient temperature and pressure changes. But what would happen if tectonic plates brought these metamorphic rocks back to the surface as well? Well, as always, they will once again be exposed to the agents of erosion. They'll be broken down and turned into sediments. But this cycle also has alternative paths. For example, any type of rock, igneous, sedimentary, or metamorphic, can be dragged back down to the Earth's interior through subduction. The enormous temperatures will melt the rock, transforming it back into magma, and, who knows, perhaps it will be brought back to the surface once again, millions of years later, turning back into plutonic or volcanic rocks. So, as you can see, the rock cycle repeats endlessly. It is truly an endless cycle that has been occurring for billions and billions of years here on Earth. But, could the rock cycle come to a stop? It seems unlikely that it ever would, but surprisingly, the answer is actually yes. The mechanism of the rock cycle relies on three main factors. First, the Earth's internal energy, which provides heat and causes rocks to melt and ascend. Second, the energy from the sun, which drives atmospheric events like rain or snow that drive erosion. And lastly, we have the force of gravity, which causes materials in elevated areas to fall towards these lower areas. Looking at these three, the force of gravity will never go away because it's a physical law of the universe. But the sun will eventually, in many billions of years, cool down, decreasing the energy required to cause weather and erosion. But before that happens, the sun will also increase in size so much that it will simply engulf the Earth in its flames. But don't worry about that, because before that occurs, the Earth's interior will cool down. When the moment comes, also billions of years in the future, the crust will become thicker, the mantle will become thinner, and convection currents will slow down. They won't be powerful enough to continue to move the tectonic plates. And then, plate tectonics will stop and will never start up again. Meanwhile, rain, ice, and wind will continue to erode the landscape, which will become flatter and flatter. All settlements will be carried back out to the oceans. And there could come a day in which all of the relief, all of the mountains, all of the land above the sea will be completely disappeared. The planet would become a perfect sphere covered entirely by water. The land masses will vanish under the seas, and all of its inhabitants will vanish. Well, not all of them.
Oh, who lives in a pineapple under the sea?
SpongeBob SquarePants!
Absorbent and yellow and porous is he.
SpongeBob SquarePants!
Anyway, we shouldn't really worry about it. It'll only happen after billions of years. In fact, it's much more likely that we will have destroyed ourselves before the solar system has a chance to destroy us. Well, by now, we have a solid understanding of the layers of the Earth and the rock cycle. You might be thinking, great, we live on a collection of rigid sections of rock floating on a giant molten ball through space. But it's not quite as simple as that. Most of the crust is covered by water, so we can only see about 30% of the Earth's surface. Today, the planet looks like this. But 200 million years ago, it was something more like this. It was a scientist named Alfred Wegener who hypothesized in the early 20th century that continents could actually move. Actually, if you just look at the shapes of the continents, some of them suspiciously seem to fit together. But in science, suspicions are not enough. Hypotheses must be justified and demonstrated. It was a scientist named Alfred Wegener who did just that. To understand how Wegener arrived at his conclusions, we must first understand the era that he lived in. Wegener obtained his doctorate in 1905. Traditionally, at that time, it had been assumed that, according to the Bible, the Earth was about 6,000 years old. Many scientists also defended that the Earth had remained geologically and biologically identical since the creation. After all, in 6,000 years, there wasn't really enough time for animals to change or for the geology to significantly modify the planet. However, James Hutton had proposed the rock cycle in the late 18th century, and for the cycle to work, the Earth had to be at least hundreds of millions of years old. And during the 19th century, Darwin also postulated the theory of evolution, which also required hundreds of millions of years in order for species to evolve. So by the 20th century, when Wegener was studying, almost all scientists accepted that the Earth was actually very old, and therefore it could have changed significantly since its origins. There already had been some scientists who proposed that, in the past, South America and Africa may have formed a single continent, but many others did not find it logical. Continents, like the ocean floor, are huge sections of rigid rock, and if the rock is rigid, it can't move, so there was no way to explain this kind of movement. Wegener published the possibility that the continents had been a single supercontinent in the past. He justified his idea by pointing to the remarkable similarities between the coastlines of South America and Africa. However, Wegener's idea was not taken seriously. The continents didn't fit together perfectly, so he faced a lot of criticism for it. He was also told that the coastline is constantly being modified by the erosive action of the sea. So even if it was true that the continents had been together in the past, the sea would have modified the coastline so much that they wouldn't fit together again. So a disillusioned Wegener began to think that perhaps he was wrong. Until, that is, he found a scientific article written by a biologist explaining that identical fossil species had been found in both South America and Africa. So, there should have existed some kind of land connection so they could move from one place to the other. Wegener began reading all the scientific articles he could find and was surprised to discover the crazy ideas that some scholars proposed to justify how species could have traveled from one continent to the other. It was proposed by some that animals had simply swam across the entire ocean. This is something that could be true for some land species, like wild boars. For example, it had been proved that they can cross the less than 20-kilometer wide Strait of Gibraltar. But swimming thousands of kilometers? That didn't sound plausible. Others suggested that animals had arrived on floating logs. While this could happen in small distances, they would eventually die of hunger and thirst in a week or month-long trip across the Atlantic. There were also those who argued that there had been an isthmus or a narrow land bridge that had connected both continents, so the animals had crossed through there. But such a narrow isthmus in the middle of the Atlantic wouldn't have lasted long before the sea made it disappear. Others suggested the existence of a chain of islands. The animals could have moved slowly, swimming from island to island. The only problem was that there was no evidence of these islands anywhere. This was the most realistic proposal of all, but it lacked evidence, just like Wegener's idea. So Wegener took the bull by the horns and started researching. For example, he discovered that fossils of the Mesosaurus, a small marine reptile that lived about 280 million years ago, had been found in both South America and Southern Africa. It was a marine animal, so yes, there was a possibility that it had swam across the ocean, but a question remained. Why didn't the Mesosaurus spread to a bunch of other areas? Wegener thought that these animals could only live in a specific climate and they should be freshwater animals, so they couldn't swim across the saltwater oceans to live in other areas of the planet. He also discovered fossils of Glossopteris, a large extinct tree that had existed about 250 million years ago. It had large, heavy seeds. It was impossible for the wind to carry them thousands of kilometers away. But things got even more complicated when he discovered that seeds had also been found in Madagascar, India, Antarctica, and Australia. He kept reading and learned that fossils of Cinnanathus, large terrestrial animals that had lived about 240 million years ago, had been discovered in both South America and Africa. And that Lystrosaurus, another large terrestrial animal that had lived about 250 million years ago, had been discovered in Africa, Madagascar, India, and Antarctica, exactly like Glossopteris. Sensing the pattern, this brought a question to his mind. What if all of these continents had, at one point, been connected? But how was it possible for plants to grow in Antarctica, which is this frozen wasteland? His brain felt like it was about to explode. This fossil evidence clearly showed that about 250 million years ago, South America, Africa, Madagascar, India, Australia, and Antarctica must have been connected in some way, because none of these common species could cross oceans. And even if they could have, the fossils should have been found in other places around the world then as well. The second main piece of evidence was that, since forests can't grow in the South Pole where Antarctica is now, the continent grouping must have occurred in a warmer zone, probably somewhere around Africa is today. He had obtained the biological evidence, but now he needed geological evidence. If the continents had been united in the past, rocks with similar characteristics and ages should be found in all of them. Some great evidence he found was between North America and Europe. He discovered that the Appalachian Mountains, mountains in the north of the British Isles, and the Scandinavian mountains had rocks with similar age and characteristics. This could be explained if, in the past, they were once united as a part of a single large mountain range that connected them, only to separate and move to other parts of the world. He also found evidence that suggested large glaciers had existed in wide areas of South America, Africa, Madagascar, India, and Australia. He was able to date these glacial remains to an age between 350 and 300 million years ago. But how was it possible that glaciers existed in these areas that now have deserts or tropical climates? This observation seemed to make no sense, unless there existed such a brutal ice age that practically the entire Earth was covered in ice. However, he also discovered that Europe and North America, at the same time, had an equatorial climate, and huge accumulations of coal had been generated in swampy areas with warm climates. These are today's coal basins of Spain, Germany, Poland, and the United States. Once again, the climates of these areas, which today are temperate, did not fit with those from 350 million years ago. So it was strange that there were glaciers in the south of Africa, but not in the equivalent latitude of the northern hemisphere, and it was also strange that regions today that have temperate climates had equatorial climates. Climates follow a north to south logic of going from colder to warmer. It made no sense that there were glaciers where there are now deserts, and that there were warm climates where there are now temperate ones. So Wegener started thinking. This was really a perplexing problem. But he found the solution. He came to the conclusion that if, as he thought, there had been a supercontinent in the southern hemisphere, with South Africa aligned just with the geographical South Pole, it would have explained the Great Glaciers. And the rest of the continents could be located near the equator, so that with this extreme moisture and heat, large deposits of coal could be formed. His theory made sense. The continents had been in different places hundreds of millions of years ago, but he still needed to explain the most important thing: how they had moved. Just at that time, Andrija Mohorovic, studying seismic waves, had shown that while the outer zone of the crust was rigid and hard, the interior of the Earth was viscous, meaning that the crust was floating on a layer melted at extremely high temperatures. Wegener was able to demonstrate that around 350 million years ago, a great southern supercontinent called Gondwana existed, while another, Laurasia, was in the north. About 100 million years later, Gondwana had moved northward, allowing life to develop in its southern zone, where species such as Glossopteris and Mesosaurus had flourished. Shortly thereafter, Gondwana and Laurasia had merged, forming the supercontinent of Pangaea, which began to break apart around 175 million years ago, eventually forming the current continents. But how did the continents move? Wegener became very excited and supposed that the continents would be more rigid than the ocean floor and could move by breaking it apart like an icebreaker. And what would cause that movement? Well, the attraction of the moon, which, just like it causes tides, could cause the displacement of continents. Exultant, he finished his book called The Origin of Continents and Oceans. He thought people would applaud him in the streets and give him a Nobel Prize or something like that. In 1924, his book was translated into English, German, Russian, and Spanish. And then the criticism started pouring in. Almost no one believed him. The truth is that Wegener was right in his observation. Continental drift was real, but he couldn't explain its origin. In reality, the moon didn't have enough force to cause it, nor did the continents just slide over the ocean floor. In 1930, he organized an expedition to Greenland, in which he sought new evidence to demonstrate continental drift. In November, under extremely harsh weather conditions, they began to suffer from a lack of supplies. Wegener and another colleague went out to get more food, but they never returned. They died in the middle of a tremendous polar storm. So, after a lifetime dedicated to demonstrating the movement of the continents, Wegener died forgotten and scorned by the vast majority of scientists who didn't take his work very seriously. And for more than 20 years, his work fell into oblivion. His biggest problem was that he couldn't explain why continental drift occurred. However, at the same time, other geologists such as Andrija Mohorovic, Benno Gutenberg, or Inge Lehmann were discovering the internal structure of the Earth, a sphere of molten magma. It was not until the 1960s when other geologists were able to explain continental drift by understanding the internal movements of the Earth. Thus, plate tectonics was born, and Wegener was able to regain his place in the history of geology. In the 1950s, our understanding of the geosphere had advanced significantly. In just about 50 years, it had been discovered that the Earth was not a solid sphere, but was composed of different layers. The exterior was solid and rigid, and the interior was molten and had extremely high temperatures. It had also been theorized that continents had moved from one place to another. However, Nobody could propose a final theory that could neatly connect both ideas. A theory that could explain the continental drift that Alfred Wegener had failed to explain. Why did the continents move? And what was the relationship between this movement and the layers of the Earth? In 1919, Arthur Holmes proposed one of the earliest models to explain plate movements, a theory that was later adapted into modern plate tectonics. His hypothesis suggested that a large convection currents in the mantle drove the movements of the plates. Let me take a step back here. You might be wondering, what exactly is a convection current? Well, basically, they're kind of like squirts of super hot magma that come from the deeper mantle up towards the crust. But, obviously, you cannot write a scientific article referring to something as a super hot magma squirt. So, Holmes decided to name it convection current. These convection currents explained the ascension of hot and less dense rock, which, when it comes into contact with the lithosphere, would drag it along, kind of like a conveyor belt. Once the material cooled down as it moved away from the core, it would sink back down into the lower mantle where it would be reheated, thus dragging parts of the lithosphere downwards with it. Holmes postulated that where these super hot magma squirts, where two convection currents coincided, an area of compression would appear. Here, at these areas, the crust would be pushed back into the Earth's interior. To counterbalance this disappearance of crust, new oceanic floor would be formed where the currents ascended. Certainly, this theory sounded good and even made sense. And, although it had some errors, it was surprisingly close to reality. But, Holmes had no evidence to support his theory. Except, something really similar to his proposal happens when we, say, boil water in a pot. These same convection currents form. But of course, that doesn't count as definitive evidence. Just because it happens in a pot in your kitchen doesn't mean it's happening deep inside the Earth. Further research was necessary. Then came along World War II, the brutal global conflict that devastated the world between 1939 and 1945. But it also brought significant technological advancements. Sonar technology, which was used to detect enemy submarines, improved exponentially during this period. Sonar essentially operates by emitting sound signals underwater, which, upon bouncing back up, allow for the identification of submerged objects. This improved technology could also be used to send signals towards the seabed itself, letting us know its depth and help with the creation of a detailed map of the ocean floor. During the 1950s and 60s, oceanographic vessels were used to do an extensive mapping of the seafloor. In 1957, Bruce Heesen and Mary Tharp published the first detailed map of the North Atlantic seabed. This study of the ocean floor revealed something quite surprising: a global system of oceanic ridges, which are large volcanic mountain chains extending for thousands of kilometers. It was also observed that the Mid-Atlantic Ridge ran parallel to the continental margins on both sides of the Atlantic. Additionally, it was found that the system of oceanic ridges was characterized by intense volcanic activity. In other parts of the ocean, even more discoveries were made. Large depressions in the seabed, known as ocean trenches, were discovered. Studies on earthquakes identified significant seismic activity at great depths under these trenches. Furthermore, when rocks were extracted from the seafloor, none were found to be older than 160 million years old. In contrast, numerous samples from continental crusts have been dated to be much, much older, up to 4 billion years old, in antiquity nearly reaching the Earth's estimated age. So from that, several mysteries emerged. Why are rocks in the continental crust so old, while those in the oceanic crust are relatively young? And why do earthquakes occur at great depths beneath the already deep ocean trenches? In the 1960s, Harry Hess tied together these new findings about the seafloor in a hypothesis called seafloor spreading. Unlike Wegener's theory of continental drift, which, due to his lack of knowledge, disregarded these ocean basins, Hess's theory focused on this submarine activity specifically. He built upon Holmes's ideas and proposed that oceanic ridges were located in areas where molten materials from the Earth's mantle ascended to the lithosphere. As the ascending materials encountered the rigid and solid crust, it was forced to move laterally, or to the side, scraping and pushing the seafloor as if it were a conveyor belt. By pulling the seafloor in two opposite directions, tensile forces would fracture the crust, creating space for new magma to seep in and form new, young oceanic crust. Therefore, the seafloor would be constantly replaced by newly formed crust. And do you know what else Hess discovered? That it was essential to give the video a like and subscribe to the channel. I swear, I was reading his super famous book, Subscribe and Like to Awesome Geohistory Videos, and he mentioned it on the first page. Obviously, I'm kidding, but if you are enjoying the video, please don't forget to hit the like button and subscribe. Something as simple as clicking like, subscribing, and also hitting the notification bell is crucial for keeping the channel going. So if you do that, thank you so much. Anyway, let's get back to Hess. He also suggested that deep ocean trenches, such as the Peru-Chile Trench, are places where the oceanic crust returns to the interior of the planet. However, while Holmes believed that both plates were compressed and both descended into Earth's interior, he pointed out that in these trenches, only the oceanic crust descended back into the Earth's mantle, leaving continental crust on the surface. Since the mantle is at very high temperature, the oceanic crust eventually melts into magma. In other words, Hess's theory explained that the oceanic crust is young because it's constantly being renewed, and while the continental crust remains afloat on the surface, forever aging. Hess's theory was almost complete, but there were still things that needed to be explained. For example, geological studies of the seafloor had also revealed geomagnetic reversals. It meant that it had been discovered that on both sides of oceanic rifts, there were bands of rocks with either normal or reversed magnetic crystallization. Fred Vine and D.H. Matthews were the scientists who managed to provide a coherent explanation for the appearance and pattern of these magnetic bands in the seafloor, and how it related to their creation and movement. During the same time that Harry Hess formulated his hypothesis of seafloor spreading, geophysicists discovered that the Earth's magnetic field experiences periodic changes in polarity. This means that the magnetic North Pole moves to the geographic South Pole and vice versa. So even though the magnetic North Pole is currently located in the north, it doesn't mean it has always been there. In fact, we shouldn't think that the geographic North Pole, which is the imaginary point where all meridians meet at the top of the Earth, shares the same location with the magnetic North Pole. In this map, we can see how the magnetic North Pole has been shifting over the past century. There have been many moments in Earth's geological history when it has eventually moved towards the South Pole. The rocks that solidified during the periods of reversed polarity become magnetized with this reversed polarity, while the rocks forming today have a quote-unquote normal polarity. Evidence of these magnetic reversals were found in lavas and sediments all over the world. Researchers measured the magnetic polarity in numerous lava flows of different ages and used that data to determine the dates of magnetic field changes. This is how the magnetic reversals of the last million years have been accurately established, as shown in this graph. The periods of normal polarity are depicted in black, while the periods of reversed polarity are depicted in white. So in 1963, Fred Vine and D.H. Matthews connected these polarity changes with Hess's theory of seafloor spreading. They suggested that, when magma solidifies along the oceanic ridges, its magnetism aligns with the existing magnetic field polarity of that time. Over the past 700,000 years, oceanic crust with normal magnetism has been created along these global ridges. However, the oceanic crust formed about 1.5 to 2.2 million years ago shows reversed polarity. This discovery further supported Hess's theory of seafloor spreading. In 1968, the concepts of continental drift and seafloor spreading were eventually combined into a more comprehensive theory we now call plate tectonics. This theory explains how the Earth's outer layer, the lithosphere, moves and changes through processes such as subduction and seafloor spreading. These processes produce most of the geological features of the Earth, including continents and ocean basins. Understanding how this geological system works is crucial to understanding the formation of Earth's topography. So, let's start with the basics. Plate tectonics postulates that the lithosphere is composed of different independent sections called tectonic plates, which sort of float on top of the molten rock in the mantle. It all starts with the cause of these plate motions. As Holmes pointed out, it's believed that large convection currents exist in the mantle of the Earth, which involve the ascension of hot and less dense rock. It continues with the subsequent sinking of cold and dense material back into the mantle. The exact origin of these currents is not entirely clear, but their existence is quite evident. In this process, the hot materials drag the lithosphere in two opposite directions like a conveyor belt. Once the material cools down, it sinks back into the lower mantle, where it heats up again. Additionally, the weight of the tectonic plates themselves contribute to this process as they sink, pulling down themselves, which continues to open up these oceanic ridges in the middle of the ocean. This cycle generates different types of boundaries, also known as faults, between the plates. There are three main types of boundaries depending on the type of movement that they experience. First, we have divergent boundaries, which are boundaries where the plates move away from each other, leading to the upwelling of material from the mantle. These type of boundaries are characterized by intense volcanic activity, because it's here where the new oceanic crust is actually formed. There's also seismic activity occurring at shallow depths here. These earthquakes are caused by tremors associated with the movement of the magma. A well-known example of this kind of boundary is the Mid-Atlantic Ridge. Next, convergent boundaries occur where the plates collide, often resulting in the subduction or sinking of the oceanic lithosphere back into the mantle. These regions are characterized by extremely high seismic activity, because as the plates grind against each other during this subduction, they generate earthquakes. Additionally, as subducted plates melt and fracture deeper down, new tremors are produced. Therefore, earthquakes can originate at both shallow and deep depths. There's usually some volcanic activity found at these boundaries as well. When carbon-rich rocks of the subducted plate begin to melt, large amounts of lighter minerals rise back to the surface, piercing through the crust and emerging as volcanoes. Furthermore, in these types of boundaries, long mountain chains often form. As we can see in this simulation, the upper layers of sediments grind against and collide with each other, folding and producing new mountain systems. This is what happens in the Peru-Chile Trench. The oceanic plate subducts beneath the South American continental plate, and the folding of the sediments and stones has created the extensive Andes mountain range. This mountain range is home to a large number of volcanoes as well. And finally, we have transform boundaries, where the plates move laterally without creating or destroying any lithosphere. In this type of boundary, earthquakes occur at shallow depths as a result of the plates grinding against each other. If the plates move in opposite directions, like in the San Andreas Fault found along the coast of the United States, the friction between them generates a significant number of earthquakes. However, if the plates move in the same direction, such as between the African and Eurasian plates, the number of earthquakes is much, much lower. These three types of plate boundaries are the basis of the theory of plate tectonics. With this model, plate tectonics satisfactorily explains the global distribution of earthquakes. On this map, you can see the areas with the highest number of earthquakes worldwide. In this other graph, you can see the earthquakes recorded in the last 100 years. However, don't panic by the increasing number of earthquakes in recent decades. The higher number is simply due to the fact that today we have more seismographs, and they're so much more sensitive than those available 100 years ago that we detect even the smallest earthquakes, something that before wasn't even possible. Experiments have shown that a tectonic plate subducting in a subduction zone can heat up very slowly and still fracture at depths of up to 300 kilometers deep. This would explain earthquakes with epicenters located at great depths below the surface. However, the mechanisms responsible for these events, called deep focus earthquakes, which are earthquakes that occur at depths of 300 to 690 kilometers, are still not very well understood. One hypothesis suggests that during subduction, increasing pressure can change the crystal structure of certain minerals, such as olivine. This transformation could cause high-pressure failures, generating the earthquakes. The absence of deep focus earthquakes at divergent and transform plate boundaries further supports the theory of plate tectonics. By mapping the seafloor of the Pacific Ocean, a series of volcanic seamounts were discovered, extending from the Hawaiian Islands to Midway Island and continuing northwards towards the Mariana Trench. The dating of this chain showed that the age of the volcanoes increased as they moved away from the Hawaiian archipelago. Hawaii Island is the most recent volcano in the chain, having risen from the ocean floor less than 1 million years ago. On the other hand, Midway Island is 27 million years old, and the Suiko Seamount near the Mariana Trench is 65 million years old. A similar situation can be observed in the Canary Islands in Spain. The oldest islands are located in the east, while the youngest are located in the west. These isolated volcanic systems in the middle of the plates, far away from both convergent and divergent plate boundaries, needed an explanation beyond the general plate tectonics theory. Volcanic systems like these, with a linear distribution along the crust, are explained thanks to what we call hotspots. A hotspot is formed when there's an upward flow of material from the mantle, often called a mantle plume. This stream of molten and extremely hot rocks can pierce straight through the thinner oceanic lithosphere and creates a volcanic area known as a hotspot. Since the plume remains in the same location while the tectonic plate keeps moving above it, new volcanoes are formed while the older ones are left behind. After millions of years, the older volcanoes erode away due to the ocean and their size diminishes. As the Pacific plate moved over this hotspot, successive volcano structures were likely formed. The age of each volcano indicates the time when it was situated above the relatively stationary mantle plume. In Hawaii, geological evidence has confirmed that the island of Hawaii is the youngest and also the most volcanically active. On the other hand, the island of Kauai is the oldest of the group and is more eroded. As we move westward, the islands are older, and many of them have been eroded to the point of disappearing beneath the waters entirely. This same concept applies to the Canary Islands. The western islands are younger, taller, and less eroded, while the eastern islands are older and flatter, and erosion has leveled their relief. After this, there was only one more discovery to explain. Wegener had proved the existence of a supercontinent called Pangaea. But recent geological studies had shown that before Pangaea, there had been several other supercontinents, such as Walbora, Columbia, or Rodinia. Thus, in Earth's 4.5 billion years of age, there was not only a separation movement, but a repeating pattern, a cycle of supercontinent formation and fragmentation. So it was then in 1968 that Tuzo Wilson proposed what would later become known as the Wilson cycle. Wilson theorized that every 400 to 500 million years or so, a supercontinental cycle would occur, bringing almost all continents together into a singular giant continent. The cycle starts with a single supercontinent that, due to its excessive size, fractures when convection current is located underneath it, causing it to fragment into little pieces. As the fragmentation occurs, new oceanic crust is formed in between. This mid-oceanic ridge continues creating new oceanic floor, and the continental sections drift apart further and further. At a certain point, the oceanic floor becomes so wide that its edges begin to cool, so at least one part sinks. A destructive boundary of sorts forms there between the oceanic and continental crust. The oceanic crust starts subducting, gradually reducing the size of the ocean. The destruction of oceanic crust causes it to shrink more and more, until the continental masses eventually come together again, forming a single large continent. And so the cycle continues. This is, of course, a very simplified version of what happens on a sphere with different continental masses and ridges and trenches with numerous plates that can push against each other. For example, nowadays, the Atlantic Ocean is growing, which leads to plate collision on opposite sides of the world. This creates a destructive boundary in the Pacific Ocean where oceanic crust is subducting it back again into the mantle. In 1977, 20 years after its original inception, Mary Tharp published a final, detailed mapping of the entire ocean floor of our planet. For the first time, we had a comprehensive view of the most remote areas of our planet, allowing us to locate all of the mid-ocean ridges, faults, and trenches that led to the discovery and identification of major tectonic plates. Plate tectonics finally came together as the theory that explained the lithosphere. So at this point, we should ask, is the Earth a special planet? Is the internal structure of the Earth important for life? To answer these questions, let's take a look at the solar system. All the rocky planets and the larger moons have a similar structure to Earth. For example, our moon has a rigid and cold crust, a partially molten mantle, and a completely molten outer core with a solid inner core. Mars also has its crust, mantle, outer core, and inner core. However, despite these similarities, there are subtle differences because in space, unlike what some people say, size does matter. We need to understand that since their formation is giant molten spheres of rock, planets have been gradually cooling down from the outside to the inside. In theory, there will come a day, billions and billions of years from now, when the Earth's crust will become increasingly larger and reach deeper into the Earth. The molten mantle will become smaller, and the outer core will also become smaller and even less fluid. Eventually, everything will solidify into a giant, rocky sphere. The interior of the Earth will be cold, and plate tectonics will stop forever. Now, back to size mattering. Smaller bodies cool down faster than the large ones. So, over the past 4.5 billion years, small celestial bodies like Mars or the Moon have cooled down faster than Earth. There is evidence that shows that both bodies had tectonic activity similar to Earth, but as they cooled down, there came a point where the crust becomes so thick that the mantle's convection currents lack sufficient strength to move the tectonic plates again. Okay, that's all fine and dandy, but maybe you're thinking, plate tectonics, who needs them? We could survive just fine without plate tectonics. What would be the problem if continents remained in the same position? You think I want my continent just ramming into another continent? That doesn't sound very convenient. Well, to answer those questions, there are two significant issues, and both are very problematic for us. The first problem is that without plate tectonics, new landforms could not be created. There would be no new mountains or any kind of uplift. So, what would happen after hundreds of millions of years if no new elevations were created? The planet would become increasingly flat due to erosion wearing away at these landforms. This might not be problematic in a place like Mars, where the presence or absence of mountains doesn't have a significant impact. However, on Earth, a planet in which the seas and the atmosphere erode the landforms, terrestrial animals would face a dramatic problem if the planet became a perfect sphere. Its entire surface would be covered in water. Terrestrial life would disappear. Only marine life would be possible. Maybe you think, okay, that's fine. I'll just evolve into a fish or a dolphin and be happy living in the ocean. But don't forget, there is a second major problem that would affect even sea life, eventually leading to its extinction. The key lies in the outer core. This layer of the Earth, highly viscous and in constant motion around the inner core, is responsible for creating Earth's magnetic field. This magnetic field, although invisible to our eyes, is essential for the existence of life on Earth. Why? Because the magnetic field protects us from solar wind, a strong stream of charged particles emitted by the sun. The magnetic field creates kind of a bubble around the Earth, acting as a shield and repelling the solar wind. Solar wind is extremely dangerous because it could strip away our entire atmosphere in just a few thousand years. In a world without an atmosphere, without gases, all of the harmful radiation from the sun would reach the surface. There would be no gases to breathe, and as soon as the water evaporates and turns into gas, it too would be expelled into space, thus breaking the water cycle. This would gradually cause the water on our planet to disappear, resulting in the loss of seas, and the most important ingredient of life itself. To get a sense of what this would look like, let's take a look at Mars, because something similar happened there. During its first billion years, Mars' interior was hot enough so that the planet could have plate tectonics, and the outer core generated a magnetic field that protected the Martian atmosphere. This allowed Mars to have oceans, a dense atmosphere, and perhaps the potential to support life during those billion years. However, as the inner layers began to cool and the outer core lost its fluidity, the magnetic field weakened. Solar wind began to blow away the atmosphere. And today, Mars is a planet with a very, very thin atmosphere, only about 1% of Earth's atmosphere. It also receives a huge amount of harmful radiation from the sun. It is a sterile and cold desert, a reminder of what Earth could be like if its interior was cold. Now that we've reached this point, we can see just how fragile and marvelous our planet is. It's an incredibly complex planet, having similarities to other celestial bodies in the solar system, but also with subtle differences that create a delicate balance that allows life to exist. Without water or an atmosphere, there would be no life. Without plate tectonics, there would be no life outside of the ocean. And without a magnetic field, there would be neither atmosphere nor water. Our planet would be a flat sphere ravaged by solar radiation and completely void of life. So thank you, plate tectonics, and thank you, magnetic field, for saving our lives. If you want to learn more, I recommend watching some of the following videos. And if you enjoyed them, leave a comment, give them a thumbs up, and subscribe to the channel. We've gone through a lot of hard work to make these videos, so doing that would mean a lot. Thank you so much for watching, and I'll see you next time.